Okay, this is Math 105, Section 1.8, Part B. Okay, now we're going to talk about circles. So a definition of a circle is the set of all points which are a certain distance, and we'll call that distance r, from a given point, and that would be the center of our circle. So think of it like this is our center point, and if we go r like this, r like this, r like this, where r is, maybe 3 inches or whatever the distance is, it's a certain distance. And if we do that in every direction, as much as we, as many different directions as we possibly can, we'll form a circle when we do that. Okay. An analogy would be, think of a dog that's got those, the leash in the yard where it's, you got the little corkscrew thing tied in the ground, and it's got a certain length of a leash. That dog's going to wear a path in a circle that's the length of the leash, because it's always going to be, pulling it to taut to bark at other dogs or whatever, chase squirrels. So that if you think of a circle, it's all, if you go that distance out from that center in every possible direction, every possible direction from that, and you go out r, and that'll form that circle. Okay, and that r we call our radius. Okay, so let's call our center HK. Let's say those are the coordinates of our center. Okay, and then we want to look at all the possible x, y's that are r away from that HK. Okay, so we're going to go look at all the xy pairs that have this distance away. So we're going to use our distance formula. This will be our distance, which is the r. And then we're going to look at the change in x. So our point is xy for all different xy points. X minus h, because this is the x here. And y minus k, because that's the y there. Okay, so we take, using our distance formula, change in y squared plus change in x squared plus change in y squared equals the distance. Okay. Now, remember, we have to take the square root of that, sorry, using our distance formula. So that's the formula with the square root. Okay. So when we have this, we can say our radius is x minus h squared plus y minus k squared square root, right? Well, we generally don't write it with the square root, so if we square both sides of this, we get this equation of the circle. See, we get r squared equals x minus h squared plus y minus k squared, where our center is hk and our radius is r, and x and y are variables. They're all the possible points on that circle. Okay, so you can see that this equation of the circle, this is our standard form, comes from that distance formula, where r is our distance. Okay, so hk is your center. Okay. If your center is at the origin, h and k disappear, right? They're both 0, so we get x squared plus y squared equals r squared. That's just when your center is 0. Okay, so let's look at an example. We're going to find equation of a circle given the radius and the center. So our first one, our radius is 3 and our center is 2 minus 5. So our h is 2, our k is minus 5, our r is 3. Okay, so we're using the form, let me just write this down, x minus h squared plus y minus k, quantity squared, equals radius r squared. Okay, so here's where our h goes. Okay. Our k is negative 5, so it's going to be y minus minus 5, which is y plus 5 squared, and then r squared is 3 squared is 9. So this would be the standard form of equation of the circle for this one. R equals 3, and center is 2 minus 5. Okay, and here's the graph of that. Here's our center. We go to 2 minus 5 to get the center, and our radius is 3, so we're going to go up 3 to get to this point, go across 3 to get to this point, go down 3 to get to this point, and go across 3 to get to this point. So you can see that we're going out 3 in every direction from that 2 minus 5 center. Okay, next example, part B, we were given this. The point P18 and Q5 minus 6 are endpoints of the diameter. What that means is, let's say we have a circle like this, and this would be P and this would be Q, and they're endpoints of diameter, which means if you draw a line segment between those two, the middle of it will be the center, okay? Because the diameter goes through the circle completely, and it goes through the center, okay? So that's definition of diameter, has to go all the way through the center. So we just have to find the midpoint of these points to find the center, okay? So the midpoint is x1 plus x2, 1 plus 5 over 2 for the x. Then we take the average of the y, so 8 plus or minus 6 is 8 minus 6, which is 2 over 2. So that gives us 3, 1. So that would be our center of the circle. Okay, and then we can use any x, y, right? But we already have the center and the radius, so we can just plug it in. So our radius is, oh, we didn't figure out the radius yet, did we? Okay. So we have to go distance from P to the center. So we're going to use the distance formula. Okay. So we'll find the distance between 3, 1 and P, or we could find the distance between 3, 1 and Q. It would be the same thing. But we're going to take 3 minus 1 squared, change in x, plus 1 minus 8 squared, change in y, to get our radius squared. Remember, that's our distance formula. So 2 squared, 1 minus 8 is minus 7, so minus 7 squared, and that gives us 53. So that's the square of our radius. Okay, remember we have to take the square root to get the distance, right? So our radius is going to be square root of 53. Okay. Oops. 53. Okay. So this is r squared, right? So r would be square root of 53. Okay. So the equation of the circle is going to be x minus h squared. Remember, h is 3, the midpoint of those two diameter endpoints. Okay. Plus y minus k, our k is 1, squared, and equals r squared. So we're following the form, and that would be the equation of the circle based on what we're given. Okay. So we just have to find the endpoint, or sorry, the midpoints of the PQ. Okay. And then find the distance from P to the midpoint. Let's say this is our P, and this is our Q. Okay. And we just have to find the distance from P to the midpoint, or from Q to the midpoint to find our radius. Because remember, the radius is half your diameter. There's 2 radiuses there. Okay. And then we can plug in the rest to get the equation of our circle. Okay, so actually, I didn't orient it right, but this would be our P, this would be our Q, and if you go halfway between, you see the radius. Okay, so our radius is 3, 1, and then this would be square root of 53, which is a little bit over 7 point something, and then here it is the other way. Okay, so there's our circle. Okay, I wouldn't ask you to graph something this detailed as far as using on a test. I wouldn't ask you to do something that was kind of this, where you have to estimate these points over here, but you should be able to do this, you should be able to graph this. Okay, now we're going to talk about completing the square. Generally, you're going to see equation of a circle that's in general form, which means it's not in the form that we want. We want this x minus h squared plus y minus k squared equals r squared, because it tells us the center, and it tells us the radius. This doesn't. So we're going to try and get this in this equation like this, in this form. But we'll do that by completing the squares on the x's and on the y's together, kind of do them, each as a group, okay? And then we're going to get a perfect square with x, and we're going to get a perfect square with y, where we have x minus h squared and y minus k squared, and then we'll have whatever we have over here is our r squared. Okay, so the first thing we're going to do is put our x terms together. So the x squared and the minus 4x will go in one parentheses, and we're going to leave room to add a number because we want to make this a perfect square. And then we do the same thing with our y terms. So we have a y squared here and a plus 6y. We'll put those together. And then we're also going to move the number over here, the minus 3, because we don't want it. It gets in our way. So we're going to add 3 to both sides. Okay, and the next thing we do, remember, is to make this a perfect square, we have to take half of the x coefficient, half of the minus 4, and square it. Okay? And then add that here. And then we'll do the same thing with the y. So we'll take half of the y coefficient, which is 3, and square it. But remember, because we did it over here, we got to do it over here too, on the other side of the equation. So we're going to add the minus 2 squared here and the 3 squared here. Remember, this will be 4 and this will be 9. Okay. Okay. And then we have perfect squares. So this thing is x minus 2 squared. This thing is y plus 3 squared. Okay. And then if I add 3 plus 4 plus 9, I get 16. Now remember, this form, x minus h squared, y minus k squared equals r squared. So this is not my radius, but my radius squared. Okay. So my radius will be 4, because I have to take the square root of this. And then my h is 2, and my k is minus 3. So my center is 2 minus 3, because I have a y minus a minus 3 there, that y plus 3. Okay. So that's how we complete the square. Now this only works when you have a 1 on the x squared and a 1 on the y squared. If you don't, you've got to make sure that you do. So you'd have to factor out whatever is on the x squared and y squared. Okay. it has to be the same number. If it's not the same number, then it's not a circle. So a circle always has the same number in the x squared and y squared, but sometimes you have to factor out a number if it's not 1. So we'll look at examples of that in class. But that's essential that we have a 1 times x squared and a 1 times y squared to do this complete the square thing. So it's the same thing we did with quadratics before, but now we're doing it with two things at the same time, with an x and with a y. You know, grouping your x squared and x together terms, grouping your y squared and y terms together, and completing the square for this one, completing the square for this one, and making sure you add those parts that you had to add to both sides. And then getting it in that standard form that we want. Okay, last topic we're going to look at in section 1A is symmetry. Okay, and symmetry is like a reflection across, in this case we're looking across like one of the axes, like the y-axis or the x-axis. So when you see symmetry, you'll see it as a graph, you'll see that reflection, kind of this thing is reflected across the y-axis. Like we could take this y equals x squared curve, this parabola, and just look at this part, and we can see that the reflection of that across the y-axis is the other part. Okay? And that happens because the distance from the y-axis, the horizontal distance, is the same in both sides. You can see that double bar means these two are the same distance away from the y-axis. Okay? And that's true for any of these points. Okay? So notice if this point is xy, if I go the opposite way horizontally, it becomes minus xy because this distance here is x here. Okay? And x here. Okay? So here I'm going x on the right, and on the left I'm going minus x. Okay? But it's the same distance. This distance is x and this distance is x. Okay? So we can say for symmetry across the y-axis, if xy is on the graph, then so is minus xy. Okay? So that we see symmetry about the y-axis. Okay? About the y-axis. Okay? If the point xy is on the graph, then so is minus xy. Okay? And a way to test symmetry algebraically is plug minus x into your equation instead of plus x and see if you get the same y. Okay, so symmetry with respect to the y-axis or across the y-axis. Now let's talk about symmetry across the x-axis. Symmetry with respect to the x-axis. Okay. Now this is just the opposite. So whenever the point xy is on the graph, then so is x minus y. Okay. So you could think of it this way. If this were our graph now, let's say that we have this thing going on, then we would also have this part going on. Okay. So if we have a point here that's xy, we have a point across the way that's x. Sorry, that's x minus y. Okay. Same x, but different y's. Okay. And then we talk about symmetry with respect to the origin. Okay. That's if xy is on the graph, then so is minus x minus y. So they both get changed to the opposite. So here's symmetry with respect to the origin. X is replaced, the equation doesn't change when you replace x with minus x and you replace y with minus y. You replace both of those. Now we can kind of see this graphically, but here's our origin. And think of this as one part of the graph. And what you can do is you can flip it across the, I'm going to use black here, but you can flip it across the x-axis, this part of the graph, like that. And then you flip it across the y-axis, and you get that other part. Okay, you see that? So that's how we can do symmetry throughout the origin, is we flip it across the x-axis and then flip it across the y-axis. Okay. Another way to look at that is think of this half as like part of a spinner. And if you spin it or rotate it 180 degrees, okay, you will get the other part. So basically you're spinning this thing. I'm going to do it the other way because I have arrows there. But if you spin it 180 degrees, you get the other part. Okay, so think of that like a spinner with the center being the origin. Okay, so that's symmetry about the origin. Okay. The other symmetry, we talked about symmetry, first of all, across the y-axis. You can see that reflection there. So when x is replaced by minus x, we get the same equation. Okay, so graph is unchanged when you replace x with minus x. In other words, you get the same equation. Symmetry across the x-axis, you replace y with minus y, and you end up getting the same equation. Okay, so that's how you showed algebraically. But you can see that symmetry across the x-axis. You can see how it's reflected, and symmetry across the y-axis. You can see how that reflection is there. Okay, and when we're trying to graph something, testing for symmetry makes our work a lot easier because it means we don't have to graph half of it. Okay, so let's look at x equals y squared for symmetry. If we replace y with minus y in this equation, we get to the same equation, x equals y squared, because minus y times minus y is just plus y squared, right? So we can say this is symmetrical across the x-axis, okay? Because when you change y to minus y and you get the same equation, you have symmetry across the x-axis. Okay, so we know we have symmetry across the x-axis, which means we only have to graph part of it, okay? Think about using y's that are positive, and we get some points here, like when y is 0, y squared is 0, so x is 0. Okay? And when y is 1, y squared is 1, so we get x is 1, so we have 1, 1, and 0, 0 is 2 points. And then when y is 2, x is 4, because we're squaring y to get x. And when y is 3, x is 9, so we have the points 4, 2, and 9, 3 as well. Okay? And then this thing would keep going. There should be an arrow there. But because we have symmetry across the x-axis, we can say, okay, this part can be reflected in this part. We don't have to plot points down here. You know, look at negative y's, because we know we have that symmetry. So we only have to graph this half, and then the rest we can figure out by symmetry. Okay. So this is x equals y squared. And if you think, you know, it's actually that y equals x squared flipped 90 degrees. You know, you think of this is y equals x squared is that parabola that goes like this, right? And if you flip it 90 degrees, okay, you're going to get that. Okay. Okay, so that's section 1.8. We'll look at some more detailed examples in class on this.